Hello. In this video, we are going to cover the central limit theorem. The central limit theorem is really an extension of what we discussed in the last video. So we really need to start there. So let's recap what we covered in the last video. So what we were doing in the last video is we were looking at possible survey results, and we decided to go through and run simulations to see like the various possibilities. All right, so we constructed simulations to show possible survey results. And when we took all of the different possibilities that we got from our simulation and compiled them together, we ended up with something that looked like a probability distribution. We actually took that probability distribution and we gave it a special name. We called it a sampling distribution. And that's because when you go through and put together a survey, you put together a survey by taking samples. All right, so that's where the name comes from. Now that distribution, when we looked at it, it was unimodal and symmetric. And as we discussed earlier in the semester, when we have unimodal and symmetric distributions, we can study them by using means and standard deviations. So we went through and we calculated the mean and the standard deviation. And we came up with a special name for the standard deviation. We called it the standard error instead of the standard deviation, but it's the exact same idea. And then once we had the mean and the standard deviation of a unimodal symmetric distribution, at that point, we recalled again another topic from earlier in the semester, and that is the empirical rule. And the empirical rule says that if you have means and standard deviation, then a certain amount of the data is going to be within one standard deviation of the mean. And so we went through and we found the probability that survey results would, we found the probability that the survey that we were talking about originally, the survey results from all the way back here at the beginning, we found the probability that the survey results would be within a certain range of outcomes. So we did all of that in the last video. That was actually quite a bit. So let's just recap with one of the examples that we did from the last video. So very quickly here. So we went through and we said if we have 1,000 people in our population, and we're talking about cat people, say 25% of the population. And we do samples that are size 100. And we do those 100-person samples. We do them so that with this is a simulation. So we're looking at simulated, what are all the different possible outcomes that if you went through and did the 100-person survey from 1,000 people, where 25% are cat people, what are all the possible outcomes? We went through and we ran this 10,000 times. So we went through and had a computer go through and do a simulation where these are the scenarios. You've got 1,000 people, 25% are cat people. You're doing 100-person samples that are selected randomly, which I didn't put here, but is actually critically important. 1-person samples randomly collected. That's a key word. Randomly collected, and then you did that 10,000 times. And when we did that, we ended up with the following picture. All right, so this was our result. So the data of our 10,000 possibilities fit onto this curve. And so when you look at this curve, there's a few things that you identify. First of all, it's unimodal and it's symmetric. And so because it's unimodal and symmetric, immediately you think, oh, cool, we could do a mean, we could do a standard deviation, and we could use the empirical rule. And so that's what we did. Okay, when we went through and calculated those using our simulation data, what we ended up with was the mean was 25%, and the standard deviation, or the standard error as we use when we're doing sampling, ended up coming in at, oh, I'm sorry, we used a formula for this in the last section. You could calculate that from the data that you collected directly, but you get a slightly different outcome. Instead, we ended up coming up with a formula for this, which got us about 4.33%. All right, and so there's our simulation. You saw the distribution of all the possible outcomes, all the 10,000 outcomes. We went through and calculated the mean and the standard errors. This is all stuff we did in the last video. So if there's any of this unfamiliar, you want to go back and watch it again. And then the last thing we did is we used the empirical rule by taking 25% and subtracting 4.33. And if you do that, you're going to get, hold on here. Well, my math doesn't look quite right. Let me pause it and take another look. All right. I broke out a calculator and checked, and yes, I did the math incorrectly in my notes, which is fantastic. Thankfully, I noticed it before somebody pointed it out. All right, so you get 20.67%. So what I'm doing is I'm taking the 25 here and I'm subtracting our standard error, and I'm going to add it. So if you take 25 and you add it, you get 29.33%. And so this, because we took the mean and we added a standard error and we subtracted a standard error, this would be the range of outcomes for one standard deviation. I didn't really leave space on either side to write that. So this is one standard deviation range. And as we know from the empirical rule, a one standard deviation range happens 68% of the time. So this is another way of saying that if we went through and took one of these 10,000 outcomes randomly, there'd be a 68% chance that it fell in this range. So that's everything we did in the last section. We used simulations to construct a range of outcomes. We went through and calculated the mean and the standard error for those outcomes. And then we calculated this range of outcomes. So this range of probability. So here's the thing. That's fantastic. That's really cool, right? But what if we wanted to do something in the real world? Like we wanted to do something where we didn't have to run a simulation, where we didn't have to go through and do 10,000 examples. Someone goes through and they do a survey, a single survey. How do we go through and use any of this, any of these results, any of this really interesting stuff on that situation? And then so that's where the title of this section comes in. And so it's called the central limit theorem. And what the central limit theorem says is that the situation that we ended up with in that last case where we started off with a situation that we went through and we ran a simulation, and the simulation happened to be, the result of the simulation happened to be unimodal and symmetric. It happened to be this fantastic looking curve that looked kind of like a normal distribution. All that stuff, the central limit theorem says that's always the case. Whenever you go through, well, not whenever, there's going to be conditions, but subject to some conditions, whenever you go through and have a survey situation, you're always going to end up with a result that is unimodal and symmetric. Your result is always going to be normal. And then you're always going to be able to go through and do all kinds of cool stuff, like you use the empirical rule, or even as we inherit from the normal distribution section in the last chapter, we can even calculate probabilities for where survey results would come in. So let's go through. That's a lot of stuff. Let's go through those one at a time. All right. So what does the central limit theorem says? So the central limit theorem says that a sampling distribution, now that's what we were just doing. We were just talking about sampling distributions. Of a sampling proportion. Now this is going to be a little confusing. I'll explain that. Of a sampling proportion is normally distributed. As long as blank. And so we'll talk about the conditions in a second. Let me just make sure that this part is clear here. So the central limit theorem says that a sampling distribution, what is a sampling distribution? It's the distribution of possible results when you go through and do a survey. All right, so when you do a survey, you're doing a sample. You're collecting a sample of information from a bigger population. So the distribution of possible results when you do a survey, that is called a sampling distribution. So what this is saying is that a sampling distribution, the results of your survey, for when you're collecting a sampling proportion. All right, sampling proportion. Now, this term kind of comes out of nowhere, but a sampling proportion is what we have been doing. That's what we did in the last section, and what we did even in the section before that. So we've been talking about proportions, percentages. All right, so if you go all the way back to the first section in this chapter, we talked about population parameters. And we said that this chapter was going to be focused on proportions. All right, it was going to be focused on population proportions. That's why all of the examples from the last section and the section before that, and even the section before that, were all related to percentages of populations. You know, so 25% of the population are cat people. In this section, we're gonna look at percentages and proportions of other things. So that's critical here, that right now, in terms of the central limit theorem, we're specifically focused on the type of parameter for the entire population that is a percentage based. The percentage of a population that's going to vote when they're registered, the percentage of a population that are cat people. When you hear percentage, also think proportion. Proportion and percentage are treated the same. So when the proportion of a population that are Republicans, the proportion of a population that I don't know, like hot dogs, the proportion of a population that believes that the Earth is round, those are all examples of sampling proportions. And so everything we've done in this chapter has been related to proportions. And so this part here, it sounds really confusing and the term kind of comes out of nowhere, but it's just giving formal language to what the central limit theorem that we're defining here, what it's focused on. And this central limit theorem, there's other central limit theorems. That's what's confusing about this. This central limit theorem is specifically for this chapter, and it's specifically for finding proportions or percentages for populations. Okay, so that's all this. So there's a lot of background. You've got to go through this because it's all this technical language. All right, so so you've got a sampling distribution. That's the distribution of outcomes of a survey for a sampling proportion, which is the proportion of a population. And we're saying that that outcome is going to be normally distributed. So the results of your survey are going to be normally distributed given a few conditions. Condition one. The survey, the sample that you're taking must be completely random, right? It's just collected randomly, no bias. Second, the sample size needs to be large enough to have 10 yeses and 10 nos. All right, so you need the sample needs to be sufficiently large to get the normal distribution. If you have a very small sample, then your outcome is just not going to be, you're not going to have enough possibilities for it to be normally distributed. All right, and then three, if the sample is collected without, so this is the same condition as the last section. So if sample is collected without replacement, population needs to be 10 times the size of the sample. All right, so given these conditions, if these conditions are met, then the sampling distribution is normally distributed. So with the mean is given by the population proportion itself, and the standard error is given by the square root where n is the size of the sample. And so to use the notation from earlier in the semester, we have n for normal distribution. You put the mean first, put the standard deviation second. And so we can construct normal distributions to represent a sampling distribution by using this notation. That's like a formula, right? So there's the formula. All right, and so what's the significance of this? So I wanted to spend a minute and talk about the significance of this. So in the last section, we went through and we did simulations, and the simulations had results that were normally distributed the result, the consequence of this is saying that that's always true. So that's really cool. That's a very powerful result to say that that's always true, of course, given a few conditions, the conditions that we put on the previous page. So it's not just a coincidence that in all of the simulations we ran, we ended up with something that was symmetric and unimodal. And when you did a large enough sample, normally distributed, that's always true. So that's the consequence, is that it's taking something that we noticed was true when we went through and did a few examples, and it says that it's always true. So that's really cool. All right. What can we do with this? Oh, wait, hold on. Sorry, there's one more thing that we're supposed to do before we do it. Before I get to what can we do with this? All right, how do we check the conditions? So we'll talk about that, and then we'll do some examples, and then that's it. All right, so how do we check central limit theorem? That's just a shorthand for that. Central limit theorem conditions. All right, so condition one. What's condition one? The sample is collected randomly, no bias. All right, so there's no way to check this from data. This needs to be checked from the researcher, whoever's collecting the information. All right, but it cannot be checked from data alone. You got to talk to the researcher. In general, the way that we're gonna handle that is this: we're just always going to assume that that there's no bias and that the information is purely random. Okay, and then to go through and find second one, what's the second one here? Sample size must have 10 yeses and 10 nos. All right, so to check on this, you take the probability, you take the size of the sample and multiply by the probability of a yes, and that needs to be at least 10. And you take the size of the sample and multiply by 1 minus the probability, that needs to be at least 10. So this is another way of saying this is the probability of a yes times the size of the population. When you multiply size times probability, that gives you the number of yeses. If you take size and multiply by 1 minus the probability, that's going to give you the number of no's, and we need that to also be at least 10. All right, and then for oh, sorry, there's one more thing I was supposed to do there. Almost skipped. So in case this assumes that P is known. If P is not known, then we can go through and do the same calculation, but we do it with P hat. So we're going to know P hat. Worst case scenario, right? You go through and you do a survey. You're going to know the result of your survey that you did. So you're definitely going to at least know P hat. All right, and then case 3, what we can do is we do n, which is the population size. That needs to be greater than or equal to 10 times n, where n is the sample size. So you got population needs to be 10 times sample size if there's no replacement. Okay, so now that we've got those out of the way, we can actually do some examples. Cool, very exciting. All right, so some CLT examples. All right, let's start off. Let's go through and for our first CLT example, let's actually go back to the problem from the last chapter. So we've got the 1,000 population, 25% cat people, 100 sample size, and this is randomly selected. Very important. I almost put elected, randomly elected, randomly selected. All right, so this is the situation. Now, again, in the last section, we did a simulation with this and we ran it 10,000 times. Now, what we're doing this time is we're not running it 10,000 times. We're trying to see whether this situation satisfied the central limit theorem. And then we can just assume that it's normally, the results are normally distributed. All right, so isn't that cool? All right, so we don't need to run 10,000 experiments to tell that. All right, so if you're checking number one, the first CLT criteria is that the samples are randomly selected. So what I'm going to do is I'm just going to put a 1 here and put a check mark. Randomly selected, that's number 1 from our central limit theorem. Number 2, we need to check whether there are 10 yeses and 10 nos. The way that you do that is you take the sample size and you multiply it by the percentage or proportion of people. So you've got 100 times 0.25. So we're going to get 25 yeses or 25 cat people. And then if you do 100 times 1 minus 0.25, then that's going to equal 75. All right, and these need to be greater than, these two numbers need to be greater than or equal to 10. So this is greater than or equal to 10, check. This is greater than or equal to 10, check. All right, and so we have 10 yeses or 10, assuming yes is a cat person, we've got 25 yeses is what we would expect if we went through and had 100 people and got the average result. And then the number of dog people we'd expect would be which is in this case is no, that would be 75. All right, and then case 3, if we go ahead and take 1,000 is greater than or equal to 10 times 100. So this, since this, if you actually look at the specific language, randomly selected people. All right, assuming you can't select the same person multiple times, then that implies that it's without replacement. And so we do want our population to be 10 times greater than our sample size. So that criteria is met. Okay, and then finally, so we've got our 3 criteria. Once you've got the 3 criteria, you can go through and say, all right, well, what's the mean going to be for our so now we're talking about p hat here. What's the mean going to be for our probability distribution? It's going to be 0.25. What is the standard error going to be? It's going to be the square root of 0.25 times 1 minus 0.25 all over 100, which is approximately 0.0433. Okay. And so, and then, we can go through and we can also say, you could do this, the resulting distribution, p hat, is going to be normally distributed. P is normally distributed. I don't have a graph for that just a second, but we're going to put one together just a minute. All right, so you got these 3 things. Then you go through and do the central limit theorem checks. Once they check out, you then do these 2 things. And now we're talking about results for p hat. So let's just, to try and tie together, hopefully you're not lost, but if you are, like, what we're doing here is we've got this information. We're collecting 100-person samples from 1,000 people where 25% are cat people. And what we're saying is the distribution of outcomes. So p hat is outcomes for those samples. The distribution of outcomes is normally distributed. And that distribution has a mean of 0.25 and it has a standard error of 0.0433. Okay. So that's cool in and of itself, but this is where prepare to have your mind blown, or maybe not. Maybe you won't think this is that exciting. But one of the things that we can do here is, what is the probability that a randomly selected survey has greater than 29% cat people? Okay, so we've got this information. We do our check. This we now know that the outcomes for our samples are normally distributed, and the question is, what is the probability that one of our survey results has more than 29% cat people? So how can we figure that out? Breakout stat crunch. All right, so once you've got stat crunch out here, we just want to go through and do the same stuff we did for the normal distribution, but now we're just applying it in the context of surveys. All right, so to do that, you first want to go to stat, then calculator, then normal. Boom, this pops up. All right, so can I move it? Nope. Let's go ahead and expand the window a little bit. All right, so now it fits. Okay, and what you want to do is you want to put the mean in here. Right, so what was the mean? We got the mean was 0.25 and the standard deviation 0.0433. All right, boom. So what that is, that graph right there, that is the distribution of outcomes. All right, that's p hat. So that gives a visual for all the possible p hat results when you go through and do your do your surveying. So you're surveying, you've got 1,000 people, 25% are cat people, you do 100-person samples, and that is what your distribution of outcomes results in for your surveys. All right, so you go through and you do those surveys and you do them an infinite number of times and you graph all the results, and that's what it's going to look like. So that's what the central limit theorem allows you to do. It allows you to go through and take a scenario, a surveying scenario where you're taking samples from a population, and it allows you to go through and say that the result of those surveys is going to be normally distributed, and you can break out some statistical software, plot the mean, plot the standard deviation, and boom, you've got the picture right in front of you. That's pretty crazy. That's a crazy result. That's really cool that you can do that. But this is where prepare to have your mind just explode. All right, so now the question is, so you're going through and you're doing those surveys. You do the surveys an infinite number of times and you get this distribution of outcomes. All right, what is the probability that a random survey is going to have higher than 0.29? You can figure that out by doing this. You put 0.29. We want to know greater than or equal to the probability. So you go through and you have 1,000 people, 25% are cat people, you do 100-person samples, you do that an infinite number of times, and then you go through and you randomly select one of those outcomes. What is the probability that that number is going to be bigger than 29%, right? So you know that the cat population, you know that it's 25%, but you're surveying. The surveys are not necessarily going to give you the exact results. So your survey results are going to be all over the place when you're surveying 100 people out of 1,000. All right. And so what is the probability that the outcome for your survey is going to be greater than 29%? 17.77%. 17.77% of the time, your survey outcomes are going to have more than 29% cat people. So it gives you some idea of what the probability of getting a high outcome is for, when you go through and you do a survey. That is wild. I mean, I don't know, maybe if the ramifications or the coolness of that is readily apparent, but we can go through and we got like 17.77%. So what is the probability that a randomly selected survey has greater than 29% cat people? Again, we know there are 25% cat people, but we're doing a survey. Surveys are not always accurate. So there's a 17.77% chance that our survey outcome is going to have more than 29%. Okay, that's just boom. My head's exploding. I don't know about you guys, but that's pretty crazy. All right, so that's an example of how we could go through, and that's a CLT example. So let's go through and do another. All right, so suppose a US election is a tight race. With each candidate having 50% in early voting. A random sample of 1,000 voters are asked whether they will vote Republican. Okay, so what are we going to do with this? Find the normal distribution for the expected outcomes of the survey. All right, so we're doing a survey of 1,000 voters. What's the normal distribution for the expected outcomes? And then what is the probability the outcome of a survey will be within 2 standard deviations of the mean? So our instructions are find the normal distribution all right, and then what's the probability the outcome will be within, what's the probability that a randomly selected outcome will be within 2 standard deviations? Or I guess in this case, 2 standard errors, because we're talking about sampling distributions. Okay, so to go through and do this, we need to apply the central limit theorem. So we have our central limit theorem checks. So check 1, randomly selected, a random sample of 1,000 voters. That's our number 1 right there. We're going to call that checked. Check 2, we need take the size of the population, that's 1,000, multiply it by the percentage chance that they gave us. So that's times 0.5, and we get 500. So that's 500 yeses. So we expect 500 people will vote Republican. And then 1,000 times 1 minus 0.5, this is for no's. We also get 500 Democrats. And so this is greater than or equal to 10, that checks. This is greater than or equal to 10, that checks. All right, and then the third case, we need to check the size of the population. So since we're talking about a US election here, we're talking about the population of the US. So the US population, or I guess the US adult population, I should say adult population, is definitely greater than or equal to 10 times 1,000, right? So the US adult population, I don't know, it's probably 200 million or something like that. 200 million, definitely much bigger than 10 times 1,000, which is only 10,000. So that checks as well. So the central limit theorem, all of our checks are satisfied. And so we know that we're going to have a normal distribution for the distribution of outcomes. And that normal distribution is going to have the mean, which is 50%, 0.5, comma, the standard error, which we can put, there's a formula for it. So it's 0.5 times 1 minus 0.5 over 1,000. And so you can go through and do the number crunching for that. It's 0.5, comma, what did I get for this? I got 0.0158. All right, so this is the answer to this. Find the normal distribution for outcomes of the survey. This is the answer to that. That is the normal outcome for the distribution. That's a normal distribution for the outcomes. All right, and then what is the probability of a randomly selected outcome is within 2 standard deviations? So here, if you just recall the empirical rule gives us a probability that outcomes are within 2 standard deviations. That's 95%, right? So that's something that hopefully you remember. But let's say you didn't remember, or let's say we wanted to go through and check it. So what we can do is we can go through and take 0.0158, subtract it from the mean twice. All right, and what are we going to get here? So our 2 standard deviation range. This is just, we're just going through and just doing some subtraction here. All right, hopefully my math is correct this time. I have 46.84, 0.4684, and then 0.5316. All right, so assuming I did that correct, what I did is I took this result and I subtracted it from 0.5 twice, and then I added it to 0.5 twice. All right, so the adding one looks right for sure. And yeah, it looks correct. All right, and so to go through and check this, we can go back to our StatCrunch. All right, so let's go back to StatCrunch and see what the probability that the outcome is going to be within a certain range. All right, so here we've got our StatCrunch, so we need to go through and change these. So let's change the mean. So the mean is 0.5. The standard deviation, we just went through and found it. It is 0.0158. We need to change this to between because we want between outcomes. And then we want to know between. So what did we end up with? We ended up with 0.4684 and 0.5316. All right, and we got 95.449974. All right, so what is that saying? Like, let's just go back, right? So the idea is you're going through and you're doing a survey. Your survey has 1,000 people in it. You're asking them if they're going to vote Republican or not. All right, you get your outcome of from your survey, and the question is, what is the probability that a randomly selected, that your survey is going to be with between 46.84% and 53.16% your result, right? So knowing that the population is 50%, is the mean is 50%. So what's the probability that you're going to be within that range? 0.95449974. So that's the probability that a single survey that you do of the 1,000 population is in that range. So just again, to just tie that together, what that's saying is that if you did a survey of those 1,000 people, you'd get results below 0.4684, below 46.8%, and above 53.2%. You'd get the tails, right? So you get the tails here. You'd get those less than 5% of the time. So the normal result of your survey is going to be between roughly 47 and 53%. That's cool. That's really neat to know that before you even do a survey, before you even collect the information, just knowing that the population is 50-50 from the early voting, and going through and knowing the sample size is going to be 1,000 people, just with the early voting results and the sample population and the sample size, you can go through and have some notion of what the range of your results should be. That it should be between 47 and 53%. All right, that's pretty cool, because then if you get something that's outside that range, that should happen rarely. Okay, let's jump back over to the whiteboard. We have there's one more example here. All right, so we have Samuel Morse. This is kind of a cool example. So Samuel Morse, inventor of Morse code. I like this example because it's not tied into politics or dogs and cats. Samuel Morse, inventor of Morse code, claimed E was the most frequently used letter? Right, in English, I guess. And the proportion of E's in English was 0.12. So 0.12, the proportion. So whenever you see proportion, if you find that confusing, to translate it into percentage, and then suddenly it becomes a little easier to interpret. So it's saying that 12% of all letters used are E's. That's what Samuel Morse said, is that 12% of all letters used in the English language are E's. And because of that, in Samuel Morse code, the E is the shortest, easiest letter to represent in Morse code. That's really amazing if that's all true. All right. Anyway, so let's say we've got all this is all data we've got, and then what we want to do is we want to check this. Let's check and see how Samuel Morse did. As a check, a random sample from a modern textbook had 876 letters and 118 were E's. For a sample proportion of 0.1347. All right, so we're using p-hat because this is a sample, right? So the modern textbook is not the whole entire English language. It's a subset, all right, and we're going through. Actually, I take it back. The modern textbook is the population in this case. So it's not all English language. The modern textbook is the population, and we're taking 876 letters from that modern textbook. There's way more than 876 letters in the textbook itself. All right, and then in our sample from the textbook, we got that the proportion was 0.1347. Again, if you get proportions a little confusing, just change them into percentage. This is saying 13.47% of the letters were E's. Okay, so the question is, what's the probability of receiving that outcome or higher? All right, so just to clear this up, just to rephrase this. So the idea here is you've got a textbook, you're going through and you're doing samples from the textbook. You're doing surveys. That's the way to think about it. You're grabbing a section from the textbook of letters and you're looking at that, at what the outcome is for that section. Okay, so you go through and you do this infinite number of times. The central limit theorem says that your results are going to be normally distributed, assuming our conditions are satisfied. And then we can then go through and calculate the probability that any single randomly selected set of letters would have a result that's that outcome or higher. That's the outcome there, 13.47%. All right, so first we need to do the central limit theorem checks. So check one, so a random sample, that's the key phrase here. That means that case one is, check one is met. Case two, we have 876 times 0.12. So we use the the p-value, assuming we have it. If we have the p-value, we use it. And so, let's see, did I write this down somewhere? Oh, here it is. So 876 times 0.12, you get about 105. That is greater than or equal to 10. So that checks. And then we have 876 times 1 minus 0.12. And that's approximately 771. That is greater than or equal to 10. That checks. All right, so we have enough yeses and enough nos. All right, and then 3, so we're just given this information, the problem. 876 letters is not very many letters relative to the size of an entire textbook. So if you take the modern textbook in terms of all the letters that are in it, it's much larger than 10 times that. So that's something you need to know, or at least have some idea of what the size of 876 letters is. I actually don't know the size of 876 letters, but it doesn't sound like very much. Maybe that's 1 page of letters or something like that. And then it's clearly a textbook is going to have more than 10 pages in it. All right. And so because of that, we do have enough. So the conditions for the CLT are all satisfied. Thus, we know we're going to have a normal distribution for the outcomes from random samples from our textbook. And that normal distribution is going to have a mean of 0.12. And it's going to have a standard error of the square root of 0.12 times 1 minus 0.12 over 1,000, or sorry, over 876. And so you get 0.12, and then the standard error, I did do the calculation for this, it is 0.010979. All right, and so this gives us the normal distribution. This is the normal distribution for our expected outcomes from picking random samples from the textbook of 876 letters. This right here, it gives us the normal distribution of outcomes. All right, let's go ahead and actually just pop that into StatCrunch here. All right, so what we want to do here, so we want 0.12 standard deviation, 0.010979. All right, we'll just leave that part there for the moment. All right, so this is what we get. Okay, and then what were we asked to do? I've already forgotten. So we were asked to find some probability. What is the probability of receiving that outcome? And by that outcome, it means this outcome. What's the probability that our proportion is going to be 0.1347 or higher? So our percentage of ease is going to be 13.47% or higher. We want to know the probability of that happening if we went through and just grabbed a random sample of 876 letters from our modern textbook, right? So there's a lot of 876 letter groupings in the textbook. We're just going to grab one at random. What's the probability? Well, that's the cool thing about normal distributions. You can find that out by just plugging the information in. All right, so let's jump over back to here. We want to ditch the between and go to just one side. We want to go to standard. 0.12, that looks good. And we want to know the probability that we want to know that it's greater than, what was it, 0.1347? Let me see, I need to check to see if that's correct. What was it? Yeah, 0.1347. All right, great. So let's jump back over. So what is the probability? So that's a pretty high amount, okay? Assuming Samuel Morse is correct that only 12%, that 12% of all actual use letters are E's, then getting an outcome from 876 letters that is 13.47% E's, that's like the that's the 91st percentile. Like that's a very high outcome. And when you get a really high outcome like that, so let's say you go through and you do a survey, okay? You do a survey, you get all the information, and then you compare it to the result from the central limit theorem, and it's like way along. It's in one of the tails. So that's the term that we use for these things off on the side. It's in one of the tails. If it's in one of the tails, so there's two possibilities. Either does bad luck, right? You went through and you selected a random sample, and your random sample was in one of the tails. It was a very high result. Okay, so that was either bad luck that you ended up in the 91st percentile, or good luck if you want a high value, I guess, depending upon what we're talking about. But that's either bad luck or your assumptions are wrong. And what thing did we assume? What thing did Samuel Morse assume? Let's go back and take a look. What did we assume? What was in here that could possibly be wrong and make it so that our stuff was wrong? Samuel Morse, inventor of Morse, claimed E was the most frequently used and that the proportion was 12%. Maybe 12% is not accurate. Okay, and so that's one way in which you can go through and use these results as well, is that if you're doing a survey and you go through and you take a sample and you use the central limit theorem and you get your probability distribution of outcomes, and then you go through and you compare that to an actual survey result that you do, and your survey result is way in one of the tails, then that suggests that either you had really bad luck or good luck, depending upon which tail you like better, or that maybe your assumption was wrong, and maybe the mean was wrong. Maybe the mean is not 0.12. Maybe it should be 0.125, right? If you shifted the mean over 0.125, then suddenly you're going to see your, your 9% probability is going to, that number is going to change, and it's going to become much higher, right? There's going to be a much higher chance that that you'd get a result with 13.47 if the proportion of E's was actually 12.5 or even 13%, then that's going to make this much more likely. So 13.47% is far enough from 12% that that's a really unlikely result. And so shifting your assumption here, would make that, would fix that. Okay, all right, so that's the video. That's the central limit theorem. That's the cool stuff you can do with it. Hope you enjoyed, and I'll see you next time.